Hey kids, welcome to section 6.2, applications of the normal distributions. Today we're going to learn how to find probabilities for a normally distributed variable by transforming it into a standard normal, and how to find specific data values for given percentages using the standard normal distribution. So remember that the standard normal distribution curve can be used to solve a wide variety of practical problems. The only requirement is that the variable be normally or approximately normally distributed. So to solve problems by using the standard normal distribution, we first need to transform the original variable to a standard normal distribution variable by using the formula. The formula for z-score, which is x minus mu over sigma. Now, we also know this formula as z equals x minus x bar over s. And that was the formula that we used when we talked about samples in previous chapters. So there are 3 steps to finding the area under a normal curve. First step is to draw the normal curve and shade the desired area. So you're going to be drawing a normal curve for every problem. Then we're going to convert the values of x to z values using the formula above. And then we're going to find the corresponding area using a table, the calculator, or software. We're going to be using the z-score table. So here is an example of how we can use our z-score information to calculate different probabilities. So an adult has on average 6.2 liters of blood. Assume the variable is normally distributed and has a standard deviation of 0.3. Find the percentage of people who have less than 5.4 liters of blood in their system. All right, so first thing we want to do is we want to draw a picture. Then we want to take a look at the information. It tells us that an adult has on average 5.2 liters of blood. So that's going to be our X bar. It also tells us that our standard deviation is 0.3. So that's going to be our S. Then what we can do is we can put in the middle of our standard normal distribution what our mean is, which is 5.2. And then I want the percentage of people who have less than 5.4. So 5.4 is going to be on the right-hand side. And if it's less than 5.4, I'm going to draw a picture like this. So now what I need to do is convert my 5.4 into a z-score. So I'm going to do z equals my value 5.4 minus my mean 5.2 and divide by the standard deviation, which is 0.3. If I do this, it gives me a z-score of 0.67. Remember, z-scores have 2 decimals, so I round to 2 decimals. Then I need to find my probability. So my probability, I'm going to look up on my z-score table what 0.67 is. And since I shaded left, I'm just going to use that value. When I look it up on my z-score table, I get 0.7486. Notice that the question asked you for the percentage. So this is going to be 74.86%. So this means that if I randomly chose a person, an adult, that there's a 74.86% chance that they have less than 5.4 liters of blood in their system. Awesome. Let's take a look at another one. This one has to do with newspaper. Each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Assume the variable is approximately normally distributed and the standard deviation is 2 pounds. If a household is selected at random, find the probability of its generating between 27 and 31 pounds per month. Okay, so I draw my picture. I put my mean in the center, which my mean is going to be this 28 pounds. Then I figure out that 27 is on the left and 31 is somewhere on the right. So I'm going to draw those vertical lines and I'm going to shade in between. Now I have to find 2 z-scores because I have 2 limits. So one z-score is going to be 27 minus 28 divided by our standard deviation, which was 2. That's going to give me a z-score of negative 0.50. Then I'm going to find a z-score for the other side. And I guess I could put these on here. 27's on the left, 31's on the right. So then I do my z-score for 31, 31 minus 28, and I divide by 2. This is going to give me 3/2 or 1.50. So there's my two z-scores, 1.5 standard deviations to the right, half a standard deviation to the left. I can now find the probability between them. I'm going to look up the two values on my z-score table, starting with the greater value, which is 1.50. That corresponds to a probability of 0.9332. If I look up negative 0.50 on my z-score table, I'm going to get 0.3085. When I subtract them, I'm going to get a probability of 0.6247. So basically what that means is there's a 62% chance that if I randomly choose an American household, they will have generated between 27 and 31 pounds of recycling a month. If I take a look at part B, more than 30.2 pounds per month. So I'm going to draw my curve. I'm going to put my mean in the center. I'm going to estimate that 30.2 is on the right and it says more than. So I'm going to shade to the right. That's 30.2. I'm going to find my z-score. Z equals 30.2, subtract 28, divide by a standard deviation of 2. This is going to give me a z-score of 1.10. Then when I look up my probability on my z-score table, since I am shading to the right, I need to do 1 minus whatever I get when I look up 1.10 on my table. When I look it up, I get 0.8643. So I need to subtract that from 1 and I get 0.1357. So that means if I randomly choose a household and measure how many pounds of garbage they had for newspaper, I'm going to get more than 30.2 about 14% of the time. So it's a pretty small percentage. Okay, so let's look at this one. Amount of electricity used by a PC. So a desktop PC uses 120 watts of electricity per hour based on 4 hours of use per day. Assume the variable is approximately normally distributed and the standard deviation is 6. If 500 PCs are selected, approximately how many will use less than 106 watts of power? Okay, well, this 120 watts is our average, so that's our X bar, and the standard deviation is 6, which is our S. Now, the whole 500 PCs, how many will use less than 106? That's what we're going to use to figure out the answer. So I'm going to put the mean in the center, 120. Now, this whole 500 PCs things, we're going to just kind of put aside for a second, and I'm looking for less than 106. So I'm going to put 106 over here on the left, and I'm going to shade to the left. So once I can figure out the probability that it's less than 106, then I can find out how many computers are less than 106. So first I want to find my z-score by taking 120, subtracting 106, and dividing by 6. This is going to give me a z-score of negative 2.33. If I look this probability up on my z-score table, since I'm shading left, I just have to take that value. So the value is 0.0099. So basically a 1% chance. Okay, so now that I know that there's a 1% chance that it's less than 106, I can find the actual number of computers by taking the 500 PCs that I'm looking at and multiplying by the probability that it's less than 106. If I do this, I get 4.95, which basically means that about 5 computers are going to be less than 106. So this question was twofold. We not only had to find the probability that a computer was less than 106 watts, but we also had to find how many were less than 106. Okay. Now let's go backwards. So a normal distribution can also be used to find specific data values for given percentages. In this case, you're given a probability or percentage and need to find the corresponding data value. So you can still use the z-score formula. Basically, this time they're going to tell you what percentage, and they're going to ask you to go backwards and figure out the value. So if we look at the z-score formula and we do some shuffling around, some uh, solving or cross multiplying, we can put like a 1 underneath the z here. And then if I multiply both sides by sigma, I get x minus mu. And then if I solve for x, notice I get z times sigma plus mu, and that equals x. That's where this formula comes from. So I can use the z-score formula, do some rearranging, and now I can find the value of a specific number. Same 3 steps. We're going to first draw a normal curve and shade. Step 2, we're going to find that z-score that goes with the corresponding area. And then step 3 is we're going to use this new modified formula to figure out what x is. So let's see how this works. So to qualify for a police academy, candidates must score in the top 10% of a general abilities test. Assume the test scores are normally distributed and the test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. All right, so a mean of 200, that's your X bar. A standard deviation of 20, that's our S. And we want the top 10%. So if I draw my graph, I put the mean in the center, which is 200. Now, where would the top 10% be? Remember that the smaller percentages are on the left and the bigger percentages are on the right. So if I want the top 10%, I'm looking for this amount right here. This is 10%. So remember, all the values underneath the curve add up to 1. So if I know that this shaded part on the right is 0.10, then I know the unshaded part on the left is 0.90. I'm looking for what that value is right there. I know it's going to be greater than 200, but I don't quite know what it is. So what we can do is find the z-score that goes with that value there. So I'm going to find the z-score by inverse norming how much area is to the left. Well, if this is my x value, to the left is 90%. So I'm going to inverse norm 90%. If I do this, I get a z-score of 1.28. That means that right here, 1.28 is going to be how many standard deviations away from the mean I am. Well, now I can actually figure out what that value is. I can take my z-score, multiply it by my standard deviations, and then add my mean, and that'll tell me what that value is. So x equals my z-score, 1.28, times my standard deviation, which is 20, and I'm going to add my mean, which is 200. So this is going to give me 25.6 plus 200. If I add those, I get 225.6. So that means if we're at the police academy and we want to only let in the top 10%, that means a candidate must score at least a 225.6 in order to be in that top 10%. All right, let's take a look at another one. This one has to do with blood pressure. For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. Assuming that blood pressure readings are normally distributed and the mean systolic blood pressure is 120 and the standard deviation is 8, find the upper and lower readings that would qualify people to participate in the study. So I need to know what the cutoffs are for people to be in this study. I put the mean in the center, which is 120. Now the middle 60% is going to look something like this. Inside of here is 60%. So I'm looking for what is the z-score here and what is the z-score here so that I can actually figure out what the blood pressure values are. Well, if this is 60% in the center, that means there's 40% total on each side. And since the two sides are the same, that means that this portion on the left is 0.20 and this portion on the right is 0.20, so that we still have a total of 1. So let's figure out what this z-score is on the left-hand side, and then we'll do the z-score on the right-hand side. So if we do the z-score on the left side, we're going to inverse norm. And I want what area is to the left of that z-score, which would be 20%, so 0.20. That's going to give me a z-score of negative 0.84. Then I want to find the z-score on the right-hand side. So I'm going to inverse norm, and I want the area to the left of that z-score. Well, I've got this middle 60% and the leftover 20%, so that's 80%. When I inverse norm, I get a positive 0.84. So now I have what my two z-score cutoffs are. I need to now find what the actual values are. So this is where I'm going to use my x equals formula by taking the number of standard deviations, negative 0.84, multiplying by how big a standard deviation is, which is 8, and then adding the mean, which is 120. So this is going to give me negative 6.72 plus 120. This gives me a total of 113.28. That's what my lower reading is right here, 113.28. Now I got to find what the upper reading is. So I'm going to do the same thing, this time use a positive 0.84 as my z-score, times 8 plus 120. This is going to give me 6.72 plus 120. This is going to give me 126.72. That is the other side. So if I want the lower reading, I got 113.28. If I want the upper reading, I have 126.72. And those are my two values. I don't have any units, so I don't have to label them. Okay. So now that we can calculate different values and percentages, let's see how to tell if things are normally distributed. So a normally shaped or bell-shaped distribution is only one of the many shapes that a distribution can assume. However, it is very important since many statistical methods require that the distribution of values be normally or approximately normally shaped. Now, there's several ways that statisticians can check for normality. The easiest way is to draw a histogram for the data and check its shape. If the histogram is not approximately bell-shaped, then the data are not normally distributed. The second way we can check to see if data is normally distributed is to look at the skewness. And skewness can be checked by using the Pearson coefficient of skewness, called the Pearson's index of skewness. The formula is 3 times the mean minus the median divided by the standard deviation. Now, if this value that you get is greater than or equal to positive 1 or less than or equal to negative 1, then it can be concluded that the data are significantly skewed. So anything between positive and negative 1 is okay, but anything greater than positive 1 or less than negative 1 is considered to be skewed. And then the third thing that we can look for is we can look for outliers. And even if you just have 1 or 2 outliers, we know that that can have a big effect on normality of a distribution. So 3 things you look at: histogram, skewness, and outliers. So let's take a look at an example. A survey of 18 high-tech firms showed the number of days' inventory that they had on hand. Determine if the data are approximately normally distributed. To do so, check the shape of the distribution, its skewness, and the presence of outliers. Okay, so if we type this data into our calculator and then do one var stat, we get a mean of 79.5. We get a median of 77.5. And we get a standard deviation of 40.5. We're going to need some of this information to calculate some of the things in a minute. We get a Q1 of 45, and we get a Q3 of 98. So first thing we're going to look at is the histogram. So if we use a calculator to draw our histogram, we enter all the values in, and then we use our calculator to draw the picture. Let's see, we end up with 1, 2, 3, 4. Okay, so we end up with 1, 2, 3, 4, 5, 6. We'll just draw a couple. 7. This is our frequency. Then along the bottom, we have number of days. All right, so we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 5 and 35.6. So I used my calculator to draw my histogram so that I wouldn't have to calculate it. And I get a picture that looks like what I'm drawing. And this was 1, 2, 3, and then 3 again, and then 4, 5, 6, 4, 5, 6, very straight. And then this is 4, and then we get 1. Okay, so here is our histogram after we draw it. If you notice, it's kind of symmetric. It definitely goes up and then it goes down. There's not a huge long tail. We'll call this fairly symmetric. If it's not obviously skewed, then you're good. Okay, so that's the first thing you need to look at. The second thing you need to look at is the skewness. So we're going to calculate the Pearson coefficient by taking 3, multiplying by x bar minus the median, and then dividing by the standard deviation. So if we calculate this value, we get 3 times, and we got some of the information off the calculator. So the mean was 79.5, the median was 77.5, and the standard deviation was 40.5. If we calculate this, we get a value of 0.15. So remember, if something is significantly skewed, the value would be greater than 1 or less than -1. This value is pretty much in the center. So the skewness coefficient tells us that it's not significantly skewed, which supports the picture that we got from the histogram. So all things right now are leading to it being normally distributed. The last thing we have to calculate are the outliers. So that means I need to do Q1 and subtract 1.5 times the IQR. Well, I need to find the IQR. I got Q1. I got Q3. The IQR is found by subtracting them. So if I subtract them, I get 53. So let's see. I take 45 and I subtract 1.5 times the IQR, which is 53. This is going to give me a value of negative 30.4.5. I could do the upper edge for the outliers by doing Q3 plus 1.5 IQR. This is going to be 98 plus 1.5 times 53. This is going to give me an upper bound of 177.5. So take a look in your table of values. Do I have any numbers that are less than negative 30.4.5 or greater than 177.5? I do not see any, so therefore there are no outliers. So if we put together all this information, it's fairly symmetric from the histogram, it's not significantly skewed from the Pearson coefficient, and there do not appear to be any outliers, then we can say yes, normally approximated or normally distributed. You could say normally distributed. So that seems to be a lot of work, but everything matches up and supports the other ideas. All right, let's take a look at our application problem. Or this is just another example of how to check for normality. So if we take a look, the data shown below consist of the number of games played each year in the career of Baseball Hall of Famer Bill Mazeroski. Determine if the data are approximately normally distributed. To do so, check the shape of the distribution, its skewness, and the presence of outliers. All right, so if I type this data into my calculator and do one var stat, it's going to give me a mean of 127.2. It's going to give me a median of 143 and a standard deviation of 39.9. It will also give me a Q1 of 96.5 and a Q3 of 155.5. While we're here, we might as well find the IQR, which is taking 155.5 and subtracting 96.5. That gives us an IQR of 59. Okay, so the first thing I want to look at is a histogram. So I'm going to use my calculator to draw a histogram for me. So I'm going to draw a histogram. Let's see, I need to go up to 10, 2, 4, 6, 8, 10. This is our frequency. Then along the bottom, I have the number of games. I have 1, 2, 3, 4, 5, 6. So there's 1, 2, 3, 4, 5, 6. I start at 34. And then I go to 59.8. So I made my calculator do this for me so I don't have to. That's 111. My bad. 0.6, 111.4, 137.2. Again, all this is off my calculator. I didn't just randomly make this up. Okay, and then I take a look at my heights. So I got 1, and then I go up to 2, and then there are none, and then I go up to 2, and then I go up to 9-ish, I think. And then I go back down to 1. So as you look at this, it looks like it is skewed because you have a tail over here on the left-hand side. So we're going to say that this looks somewhat skewed. Hopefully we can get the other information to support this idea. Okay, if we look next at the skewness, we're going to calculate the Pearson coefficient by taking 3 times the mean, which is 127.2, minus the median, which is 143, and divide it by the standard deviation, which is 39.9. This gives us a value of negative 1.19. Remember, if the value is greater than 1 or less than negative 1, then it is significantly skewed. So since our value is less than negative 1, we can say that this is significantly skewed. This supports the idea from the histogram that it is skewed. Okay, let's take a look at outliers. So I'm going to do Q1 minus 1.5 times the IQR. So that's going to give us 96.5 minus 1.5 times 59. This gives me a lower boundary of 8. If I do the upper boundary, Q3 plus 1.5 IQR, this is going to give me 155.5 plus 1.5 times 59. This is going to give me an upper bound of 244. So if I go back to my data, is there anything smaller than 8 or greater than 244? I do not see any outliers. However, that's okay. We don't have to have outliers in order to have a skewed distribution, but together, the somewhat skewed histogram, the significantly skewed Pearson coefficient, and no outliers is still going to say, no, the data are negatively skewed. So we have 2 of the 3 that are supporting the idea that the data are negatively skewed, not normally distributed. All right, we've got one more slide here. Assume you are thinking about starting a Mensa chapter in your hometown, which has a population of about 10,000 people. You need to know how many people would qualify for Mensa, which requires an IQ of at least 130. You realize that IQ is normally distributed with a mean of 100 and a standard deviation of 15. Complete the following. 1. Find the approximate number of people in your hometown who are eligible for Mensa. Well, if you're eligible for Mensa, we need our value of your IQ to be greater than or equal to 130. So let's calculate the probability so that we can calculate the number of people. It's a mean of 100. I want the probability that you're greater than 130. So I need to find a z-score. 130 minus 100 and divide by the standard deviation, which is 15. This is going to give me a z-score of 2.00. Then I need to calculate what the probability is that it'll be greater than 2.00. To do so, I need to subtract from 1 my answer because I'm shading to the right. So when I look up 2.00 on the z-score table, I get 0.9772. So when I finally subtract it, I get 0.0228. So the probability that a person is at least 130 in their IQ is about 2%. So if I want to find the actual number of people, I can take how many people are in the town, which is 10,000, and multiply by the probability of being in Mensa, which is 0.0228. And if I do this, I get 228 people. That's how many people would be in Mensa in my hometown. So, is it reasonable to continue your quest for a Mensa chapter in your hometown? Well, are you going to have 228 people in your hometown? I mean, that seems like a pretty high amount of people in your town to be super smart to start this Mensa chapter. So, I'm going to say no, it does not seem reasonable. That's a lot of people to have to recruit. Does not seem reasonable to find that many people. So, how could you proceed to find out how many of the eligible people would actually join the new chapter? Be specific about your methods of gathering data. So, what you could do is you could call people in the hometown and ask them if they would want to join it or not. You'd want to make sure that you call home phones and cell phones. Maybe you go to their house and ask them. So we could call home and cell numbers, ask to speak to an adult, and then ask about their willingness to join Mensa. This is not going to be a foolproof way, but it's going to be a good start. You could also go door to door and knock on people's doors. Last question. What would be the minimum IQ score needed if you wanted to start an ultra Mensa club that included only the top 1% of IQ scores? So notice that the way Mensa is set up right now, it's about 2.28%, but I only want the top 1%. So we need to figure out what that value would be. So if I put the mean in the center, which is 100, and I'm looking for the top 1%, so that's going to be this shaded region over here. That means the unshaded region is going to be 99%. So I need to find what that z-score is that's going to give me that value. So my z-score is going to be found by inverse norming the values to the left which is going to be 99%. And this is going to give me a z-score equal to 2.33. Then I can take and find my x value that goes with this by taking the z-score 2.33, multiplying it by the standard deviation, which is 15, and then adding the mean, which is 100. If I do this, it'll give me a Mensa score of 134.95. This would be the score that people would have to achieve in order to be in this Ultra Mensa Club. All right. That is the end of lesson 6.2. If you guys have any questions, let me know. And as always, keep calm and keep trucking.